So on to the next vector subspace that we associate to a matrix. This one is called the row space. It has a seemingly too simple definition to possibly be useful. That is not true, though. The row space of a matrix is simply the span of the row vectors of the matrix. So we look at these row vectors for a given matrix, consider them as vectors, look at the span, all possible linear combinations of those row vectors. That is called the row space, and we denote that with this notation RS for row space. Okay, so very surprising theorem that we're going to note first, and that is that if you have any elementary matrix and you use that elementary matrix to multiply by matrix A, it doesn't affect the row space. So the row space after you multiply by the elementary matrix is exactly the same as the row space before you multiplied by the elementary matrix. So in other words, doing a row operation does not change the row space. Very surprising that this would be the case. The proof is pretty much this argument right here. So realizing that both of these matrices, A and EA, in each case, any linear combination of the rows of one of those matrices is also a linear combination of rows of the other matrix. And let's see in a specific example. Keep in mind the matrices are A and EA. Let's give ourselves a little bit of space to work here. EA is E times A, and think about how matrix multiplication works. What we know from matrix multiplication is that one of the rows of this matrix is some linear combination of the rows of this matrix, where I use this row here as my coefficients. Well, likewise, this row is this linear combination of these rows. So now let's consider, suppose I have a vector that is in the row space of EA. If I have a vector that's in the row space of EA, it's a linear combination of these vectors. And thus, I'll write this down, if I have a vector that's in the row space of EA, then it's a linear combination of these vectors, which means it's a linear combination of linear combinations of these vectors. And as we have previously discussed, a linear combination of linear combinations is a linear combination. And that means that V must be a linear combination of these rows, and therefore it must be in the row space of A. You can turn this argument around backwards to show that the inclusion goes the other way by making the observation that A is E inverse times EA, and the argument then turns around in the other way. Previously we showed this, and now looking at this other way, it will show that. And that'd be a good exercise for students to fill in the blanks. Okay. All right, so amazing result, and that even though that this row space thing is defined in kind of a weird way, it has this remarkable property that it's preserved by elementary matrices. Okay. So this actually gives us a great means for computing a row space, and specifically finding a basis for a row space. And that's because even though the row space of a given matrix might be hard to understand, when you look at this matrix and think about the span of these row vectors, well, it's hard to tell which of these rows might be a linear combination of the other rows, who knows. However, the row space of the reduced echelon form, this is easy to understand. These rows that have pivots in them are clearly independent because of the pivots. Right? There's no way that these two rows could be related by linear combination because of where the pivots are. And The row of zeros at the bottom, well, it's a 0 vector. Obviously, I wouldn't include that one. That couldn't be part of a basis, so we throw that away. What I have then is a pair of vectors that's independent and clearly spans the row space of the reduced row echelon form, which means it also spans and therefore is a basis for the row space of A. It's a wonderfully convenient method. If you want to find a basis for the row space of a matrix, you row reduce it, and then the non-zero rows, what you might call the pivot rows, are your answer. That is a basis for your original matrix. Okay, very convenient method. All right. So we can draw some conclusions about the dimension then of the row space. Come back up here. Well, we have the observation. We get a basis vector for the row space. We get one for every pivot. You can see that right here in our process. For each pivot, there is a corresponding non-zero row, or again, what you might want to call a pivot row. So you get one dimension for each pivot. Fine. So the dimension of the row space is the rank. It's the number of pivots. Okay, but wait a second. We've also previously observed that you get a basis vector for the null space, one for every free variable. We observed this in the previous lecture. One for every free variable. Well, you can think of the pivots. Of course, each pivot corresponds perfectly with a pivot variable or a pivot column. So what we have then is a partitioning of the columns, each making contributions to one of these vector subspaces. The columns that do have pivots, each one contributes in its own way a basis vector and therefore a dimension to the row space. The columns that don't have pivots, by corresponding to free variables, contribute to the dimension of the null space. Grand total then, if you add their dimensions, you get the grand total number of columns, otherwise known as the number of variables in the system, and that gives you this result. And it's the dimension of the null space plus the dimension of the row space is always equal to the number of columns in the matrix. Really surprising result. Certainly if you look at how the null space is defined, and then you look at how the row space is defined, it's not at all clear if there's any connection between these two things. And yet their dimensions are very, very closely related in terms of how they add as a result of this observation. It's a wonderful little result. Okay, so moving along, there is an even stronger connection. This one's not in the textbook, but great result. Not only do the null space and the row space relate by way of their dimensions, they are always perpendicular to each other. Really surprising, but not hard to prove. Nice little argument here. Pick a vector in the row space. Let's not forget what the row space is. It's the span of the row vectors. So here it is. There's any vector in the row space has got to be some linear combination of those row vectors. And we're using R1, R2, etc. through Rk to represent the row vectors. Okay. Now pick a null space vector. Any null space vector. Well, the null space is characterized by vectors that have this property. A vector that, when multiplied by the matrix, gives you 0. Now, let's not forget exactly how to expand this. What does it mean to multiply a matrix times a vector? One of the different points of view, of course, that we've talked about. Here, I'm going to take the point of view that we're looking at the rows of the matrix A dot this in vector. And it says here we get 0 for all of those. So that matrix vector product being 0 tells me that Ri dot in is always equal to 0. Okay, that being said, my assertion is that these two spaces are perpendicular. I'm going to show that by showing that these two vectors are perpendicular. An arbitrary row space vector, an arbitrary null space vector. I'm going to show they're perpendicular by computing their dot product and getting 0. And the way I'm going to compute their dot product, well, I will take row space vector. There's that. Do a little distributing. That turns into this. And then I take advantage of the fact that that is clearly 0 and that's clearly 0. In fact, all of the remaining dot products in here are 0. And therefore I get 0. So as desired, these two vectors are perpendicular, and therefore these two vector spaces are perpendicular. Really interesting result. And again, shocking that two things that are defined in such very different ways would have such a strong relationship between them by virtue of being perpendicular. Okay. So there are some more things that can be proved about the relationship between the null space and the row space. We won't be spending time on these in Math216. It turns out that not only is every null space vector perpendicular to the row space, but furthermore, the null space is all of the vectors that are perpendicular to the row space. It's the complete collection of vectors perpendicular to the row space. Sometimes this is called the orthogonal complement of the row space in this case. Okay. And vice versa. The row space is the complete collection of all vectors that are perpendicular to the null space. Slightly stronger than facts and what we just proved. A little bit of trouble to prove them, not so bad. We're just not going to spend time on Math216 on those. Furthermore, if you have a basis for the row space and a basis for the null space, then if you combine those, you get a basis for Rn. Certainly we know that the arithmetic works out here. We know that the number of these vectors adds up to n. We argued earlier that these dimensions add up to n, and therefore the number of vectors in the basis adds up to n. So this is the right number of vectors, and there's just a little bit more work that has to be done to show that this list is independent.